This is the Math 1401 Zoom meeting for March 1st, Monday. A little late tonight, 9 p.m. Just doing section 5.4 this week, practice problems 3 through 31 odd. No quiz this week. Test 3 will be given on Friday, due Sunday, be non-proctored, and it will have the same format as test 1. Covers 5.1, 5.2, 5.3, and 5.4. So there's no separate quiz just on 5.4 this week because we are at the end of the chapter of probability, chapter 5, and we will just do the test for the end of this week. And you'll have 20 problems, 5 points each, and you will put your answers, true or false answers, on the Google form that we send out with the test. For MyLab Statistics, again, from the study plan, all chapters, section 5.4, which is conditional probability and the multiplication rule. So under conditional probabilities, we've got these problems. And under compute probabilities using the general multiplication rule, we have these problems. I believe there's 18 of them. So just email me the percent of these 18 problems you get correct for your MyLab grade for this week. No quiz grade this week. Oh, we have a participant. I don't have your name in front of me. Would you care to introduce yourself?
Hi, I'm Hallie.
Okay. Do you have a question tonight?
No, just here to learn the next 5 point, whatever one we're on, the 5.4.
5.4, okay. 5.4 is an extension of 5.3. Just to remind everybody of 5.3, what we have is we had the keyword and we had A and B independent. And therefore the probability of A and the B, and this means they occur together. A, B occur together, they simply multiply. And probability of B. Oh, I've been up since 6 this morning. My kid started school, yeah. Try to write it again. Probability of B. They simply multiply. It's really nice and simple. So what we do in 5.4 is we relax independence. All right, so A and B are not independent, which means A and B are dependent. Which means when A occurs, it affects whether B will occur. Whereas up here, A occurs, has no effect. When A occurs, no effect on B at all in independence in 5.3. But in 5.4, yeah, the A happens, it'll affect whether the B happens. Now this leads to the key word given. So we start with the probability, and usually they use B given and A. So this means A happens, find the probability B happens or occurs. So what I do is I diagram this out. I draw a fraction bar. The word or letter after the word given occurs on bottom. Always. But then the A is happening, you've got to have, then you're trying to find the probability the B is happening, the A is happening. That means they're occurring together. So you have both on top, which means the probability of A and B. So you're taking the probability they're occurring together, dividing by the probability of just the A happening. Okay, this is formula one, the given formula. The given formula. By the way, you'll also see this, the gibberish for this, it'll be written and they use a straight line for the word given. And it means, again, the probability A and B over just A. You'll see this notation used a lot. Oh, we've got 2 participants now. Appreciate both y'all coming out. I apologize, I can't see who you are. I don't have your names on the screen. All right, but this leads to a second and formula. Here, we're going to solve for probability A and B. Well, if you're going to solve for this, can you tell what you do to both sides? You're going to clear your fraction, cancel this and this, and that means you got to do it to this side. All right, so I'll rewrite this and switch sides. Leave this up. Switch sides. Probability of A and B, can you see, is just the first one. But then multiply by the probability the B happens given the A happens. This is the 5.4 and formula. Once again, to compare it to 5.3 and formula, probability of A and B, you have the first one just like this, but then you have just the second one. So I know this all seems like a little bit like gibberish until you see some examples, but you can kind of see it doesn't matter that in 5.3, it doesn't matter that the A has happened. It has no effect on the B. But up here it does. The A happening or occurring affects whether the B will occur. And these are the 2 formulas for for and. The 2 formulas for, just to recap it, the 2 formulas for 5.4, the given formula. Probability of B given A is the probability, probability of A and B. My pen is dying. Got another one. Probability of A and B over just the probability of A. And then the and formula probability of A and B is equal to the probability of A, the probability that B happens given the A. Again, you can get this one by multiplying this one by the probability of A. All right, this probably looks like complete and total gibberish. So after you see a few examples, you'll realize it's not as bad as it looks. Any questions so far? Anybody want to say anything?
I'll look forward to the examples.
What now?
Looking forward to the examples on how to apply them.
Oh, okay. Well, we'll just charge in. It starts on 5.4. We'll start down at problem 3. All right, E and F are two events. Notice they don't say they're independent. If they want them to be independent, they will tell you they're independent. If they don't mention anything about independence, you can't assume they're independent. And they give you the and of them. E and F is 0.6 and just E is 0.8. What is this? That's read F given E. So let me write down this given information. $5.4 268. Problem 3. Probability of E and F 0.6. They're using E's and F's instead of A's and B's. And just E 0.8. Find probability of F straight line E. This is read given. All right, from what I just did, hopefully you diagram this out. The second thing always goes on bottom. Both on top. Usually we switch it and do it in order, E and F. So then once you realize how it's diagrammed out, it's easy enough to plug and chug the numbers. So E and F is 0.6. This is a straight line. Just E itself is 0.8. Notice how your top is less than your bottom. It's going to come out less than 1, as it should, as all probabilities should, less than or equal to 1. You may know 6/8 is 3/4 or 0.75, but we'll divide it out. 0.6 divided by 0.8 is 0.75, 3/4 in other words. So these first little exercises are just exercises in using these formulas. Okay, number 5, we should mention a little switch in notation. They're using this formula, N, E and F. Notice that's not a probability, that's a number, 420. And N of E 704, again, another number. What is probability of F, again, given E? Okay, this notation, this N is read number in E and F. And this is read number, in effect, they're frequency numbers in event E. In E, you diagram it out exactly like we did before, probability of F given E. Second one goes on top, except we'll write number in E. Number in E. And then both of them are on top. Number in E and F. And now you can see your 420 goes on top. That's the number in E and F. Number in E is 740. And again, this will come out less than 1. 420 divided by 740, 0.5675. Yeah, I mean, you can keep how many places you want, 5, 6, 7. I might call it 5, 6, 8. Questions about that?
I don't have any.
Okay, so what happens is by number 11, they start into some word problems with this, and that's where things can get a little tricky. And they can get long, so I won't copy them all out. And sometimes they don't explicitly use the word given, it's implied. Why don't we charge into number 11? It's about cards. Suppose we have a single card selected from a standard deck. All right, they give you a bunch of little sentences. I wish they'd spread this out in part A, part B, but they don't. They just give you little sentences. So what is the probability the card is a club? All right, let's just stop there. So 11, find probability of a club from a deck of cards. Everybody's savvy enough about cards to know that there are 13 clubs in the deck,
Yes.
52 total. And I think you'll find that's 1/4 or 0.25. Clubs are a quarter of the deck. Hearts are a quarter. Every suit's a quarter of the deck. So you get the same probability whether they'd asked hearts, diamonds, or spades. Questions about that?
I don't have any.
Okay, 13 goes into 52 4 times. 13 times 4 is 52. Okay, then they ask another question. This is where things get tricky. Suppose your single card is drawn. I can get it up here without. But you're told the card is black. See, that's what's given. Even though they did not technically use the word given, if you're told it's black, you assume that that's what you're given. There's the 0.25 for the first answer. What is the probability that you are drawing a club? So I'm going to put this in the wording of the formulas, even though it's spread out in sentences. So what they're really having you find is the probability that you're drawing a club given that it's a black card. Okay. Remember, you were told it was black. That means it was given that it was black. All right, I'm going to do method 1, probabilities. All right, so I'm going to write this. We're not using E's and F's or A's and B's. I'm going to diagram it out, though, just like I showed you. Club, given, black. The second thing goes on bottom, the probability of a black card. Both go on top. I'll switch the order, black and club. Questions about this?
Are we to leave it like this or apply the numbers to it?
Yeah, that's the second thing, is just use the numbers. But I'm gonna show you what happens when you use the probabilities, because it explains why you can just use the numbers. If you start with the probability of a black, y'all know how many black cards are in the deck?
26.
26 out of 52. That's the probability of just drawing a black card. A half, in effect. Black cards are half the deck. All right. Black and club, well, there are 13 cards that are black and club out of 52. So that is the top one, and the black is this one. If you know your rules for fractions, you take the top and you multiply by the flip of the bottom. Remember, you flip and multiply. And look what happens. Your overall totals cancel. You're left with 13 over 26. That's a half, or 0.5. You probably could puzzle that out without knowing any formulas whatsoever if you're a real card shark. If you're told it's black, you only got to be looking at black cards. There's 26 of those. And then the probability that you're getting a club, well, club, there's 13 clubs, 13 out of 26, bingo. So yeah, I've got people, I can't write the formulas, but I can think about it, and puzzle it out. Hey, that's great. You'll get full credit for doing that. It's just that I can't teach it that way. It's tough to teach jiggering in your head. You can't read neurons floating around my head. So that's why we always teach it with the formulas. Questions about that?
Yeah, where I got a little bit, if I have done it without you showing the example, I would have failed, because I thought black and club will be a total of all the black cards in the whole card, which will be 13 over 26 as well. But
yeah, exactly. There's people who see that instantly, and they're card sharks. They play cards, see it. That's great. You can do it that way. I've got other people don't even know what a deck of cards is. So they've never seen a deck of cards in their lives. So it's hard for them to do that way. So that's why we show them the formulas. Now, the number version of it, here's number 2, the method 2, using the number version of this, you'd have probability of club given black. Let's do it again. The second thing from the number black. That'd be the number of black cards versus the number of black and club. That is the number of black and club cards. Well, the number of black cards is 26, and the number of black and club cards is 13. Number of cards that are both black and club, there's 13 of those, and there's your half instantly. And so you don't have to go through the rigmarole of canceling out the overall totals like you would in probabilities. So yeah, this provides a shortcut. In a lot of problems. All right, y'all want to see a few more examples?
Yes, please.
All right, they completely switch gears in 13. $268.13. Talking about Chicago. And in the month of June, 37% of the days are cloudy. But also in the month of June in the city of Chicago, 21% of the days are cloudy and rainy. All right, let me write that given information down. So I would write it this way: the probability of a cloudy day is 0.37. 21% are cloudy and rainy, so the probability cloudy and rainy. So it's doing both, showing a lot of clouds and it's raining. That's 0.21. Whereas just having clouds, cloud cover is 0.37. All right. What is the probability? Here's what they want you to find. What is the probability a randomly selected day will be rainy if it is cloudy? All right, so they use the word if instead of the word given. They could have just as well said given it is cloudy. You know, they should word them a little more consistent to keep the confusion down, but I didn't write the book. So I would really word it this way: find probability it is rainy given cloudy. And once again, we diagram it. The second thing goes on bottom. The probability, don't really have a chance to do number here because you're not given the individual numbers. You're given straight probability. So this is going to work off the straight probability formulas. The bottom will be the probability of the thing after they were given, probability cloudy, and the top will be both, probability cloudy and rainy. And now you can see straight how to plug and chug. The small number goes on top, bigger one goes on bottom because it's got to come out less than 1. If people get confused and they'll switch it, and that should be obvious that there's something wrong. You do it this way, it's greater than 1. No way it can work. Probabilities are between 0 and 1. That was section 5.1, first rule. Always. Good. It's a good way to check yourself. Coming out bigger than 1, you're screwing up. So 0.21 divided by 0.37, 0.567. I'll call it 568. Questions about that? Less than or equal to 1, as it should be. Now you can still screw it up and come out less than or equal to 1, I suppose. But if you're coming out bigger than 1, you're definitely screwing it up. All right, why don't we jump down to one like 17? There's a lot of parts to it. We won't do all the parts, we'll leave some of them for y'all. But this is about polling adults. And it's a long problem with a lot of numbers. Recent Harris poll. I don't know if y'all have your books or you can see it. A random sample of adult Americans, and they defined that 18 years and older, was asked, when you see an ad emphasizing that a product is made in America, are you more likely to buy it, less likely to buy it, or neither more or less likely? You don't care. So the results of the survey are here, and they broke it just down by age. Again, these are adult Americans. I guess it could be men or women. In the age 18 to 34 bracket, it's, the most common was they didn't care. And the second thing was more likely. 35 to 44, more likely to buy it because they knew it was made in America. Same thing with 45 to 54, 360. Clear majority said they would, and a clear majority 55 plus. Okay, now this is our first brush with table problems, so we should make a point of this. They've collected the numbers here, and then they've totaled it horizontally to get these totals over here. And then they've totaled it vertically to get these totals down here. Here's the rub. Let's pretend we don't know this corner number. Do you understand that if I total the totals here vertically down and across, they've got to come to the same number, in this case 2160. If they don't, you're screwing up. Oh, we've got another participant. Sorry, I can't see your name. Let me just prove that to you. So if I total the total vertically here, 1329, add 66, add 765, I get to 2160. And if I total these numbers across, 542, 536, 546 plus 536, and there's 2160. So that will be true on a bunch of table problems. All right, let's see if we can try what they're going to ask you about without me, copying down, wasting your Zoom time copying that problem down. They do use the word given here. What is the probability a randomly selected individual is 35 to 44, given that they're more likely to buy a product made in America? All right, let me try to shorten it up without writing out all those words. This is problem 17. We're on page 268. Problem 17, part A. Find probability you're 35 to 44, and they do use the word given. More likely. It's supposed to more likely, L-I-K-E, okay, to buy a product made in the good old US of A, America. All right, well, once again, it's going to equal a fraction. And this second thing is what's on bottom. I'll just word it product more likely. Probability of more likely. All right, and the top will have both. Probability more likely and your 35 to 44. Now I've worded it as probabilities, and I can word it that way. You want to see it worked as probabilities, or do you want me to shorten it up and show it to you as numbers? Because you can do this one with just numbers.
Numbers, please.
Just no. See, this would be the same thing as if you did the number of both, more likely, and your 35 to 44 over on bottom, the number of just more likely. All right, so now you got to look at the table and see if you can figure out your numbers. What is the total number of people more likely? Can you tell it's 1329?
Yes.
Okay. So this number is 1329. Now you need both. You need the number more likely, that'll come off the top row, and their in the age range 35 to 44. So they're both more likely and 35 to 44. Can you tell that would be
329.
329? So this top is 329. I won't write it out, but if it was up here, your top would be 329 divided by the 2160, and this number would be your 1329 divided by your 2160. See, that would be the probability you're more likely. You'd be the number more likely over the total number of people in the survey, 2160. Same thing up here, number more likely and 35 to 44 over 20. You see how the 2160s are going to divide out and give you this? If you flip this around, your 2160s cancel and you're left with this 329 divided by your 1329. The book will usually get a decimal for that. 0.24755, we'll call it 0.248. Questions about that? Why don't we try another one like 19, maybe the first part of 19. There's a real uplifting problem, cheerful, driver fatalities. So they've broken down the number of fatal crashes in 2013 by gender, male and female, and by the day of the week. You can learn, if you look at the numbers and think about them really closely, you can learn a lot. Take a look and just compare the number of male fatalities of drivers, male driver fatalities versus female. You notice anything? Take a look at the totals if you really want to see it.
Men are worse drivers.
There's a lot more male driver fatalities than female driver fatalities. Can you see that? In fact, it's about double. You can almost conclude it's about twice as likely there'll be a male driver fatality in a crash than a female driver. Now, why would this be?
Because there are more male drivers.
Yeah. If men and women get together, more than likely the women will let the man drive. It was true in the 1800s with horses and carriages, and it's true now with, with cars. Just, I don't know, human nature. Okay, you ready to try one of the problems? Same idea. You can total down this way. This would be the total males. You can total vertically. This would be the total females. Then they total both of them across, and this would be the total Sunday crashes, total Monday crashes, etc. And if you total the totals vertically here, horizontally here, you've got to come to that same number in the corner. Anybody want to see it done, or do we all believe?
We believe.
You believe. All right. Try part A. Part A. Okay, again, you've got, it's not worded with the classic, they do not use the word given here exactly. So you've got to read this and think what is given. Among Sunday fatal crashes, what is the probability a randomly selected fatality is female? Okay. What they're asking for, what you define, that's the first thing in the given. Do you see that among the Sunday fatal crashes, that little phrase? That's what's given. It's given Sunday fatal crashes. Find the probability you're female. So I'll write it out that way. Find the probability we have a female fatality given a Sunday crash. Everybody get that? And once again, I will draw out a fraction and I will put the second thing on bottom, and we can use the number notation, number of Sunday crashes. And we need both of them on top. Number of Sunday crashes and your female. All right, can you figure out the number of Sunday crashes? Total of
64.
Sunday crashes. Can you see it's
6,430.
6,430. And then now you want Sunday crashes and female. So Sunday crashes looks across this first row. And the ones that are involved in Sunday crashes and their female is
2,287.
2287. Notice I'm less than or equal to 1 here. I'll divide it out. 2287 divided by 6430.35. 5, we'll call it 356. In other words, in effect, the number of female fatalities on Sunday crash is about 1/3 of the number of male fatalities on Sunday crashes. All right. We're at 40, almost 45 minutes. There's one other little subject that they cover in this section. I'll show it and then give you maybe one example about it. I know it's getting late. It's another way to show independence. And the two phrases, P-A, that you could say illustrate independence. All right. Phrase 1 will say without replacement. Phrase 2 with replacement. And sometimes they, again, don't use these phrases, but they can be implied. Okay, let's see. Pick one here. The easiest way to illustrate this is like, 29. The tulip problem. Bag of 30 tulip bulbs purchased from a nursery. Well, they don't really use the phrases. Let's see. Should I use the phrase? Okay, let me do 23 first. It's a little easier, fewer numbers, and they do use these phrases. That would be easier to understand. 23. Back to cards. 2 cards are randomly selected from a 52 card deck. I'll give it up so y'all can see a little better. What is the probability the first card is a king and the second card is a king if you're done without replacement? Okay, so let me illustrate this, page 269, 23. This is with cards. Find probability you pull 2 kings without replacement. Okay, here's the way it works. 2 kings. No replacement. You take 2 slots. First one's a king, second one's a king. All right, first one has the full deck. Would you all know what the probability of pulling a king out of the deck is?
1/52.
Well, how many kings are in the deck? There's
4/52.
out of 52. Okay, here's the rub. The phrase no replacement without replacement. When you go to do the second poll, you assume a king has been polled. This one is a king. You assume it was polled and not replaced. So there's a king missing. So if there's a king missing from the deck, what would the chance of pulling a king be?
3/51.
3/51. Very good. There'd be 3 kings left. And since there's a card missing from the 52 card deck, in other words, this probability depends on this. These probabilities are dependent. You can call that 12 over whatever those two numbers are. Usually we just get a decimal. I'll just take 12 and divide by 52, and then divide that by 51. 0.00452. Okay, now that's part A. Part B, find probability pull 2 kings. They say with replacement. Probably guess what's going to happen with that phrase. Again, 2 slots. First one's a king. 4 kings out of 52. I'll show you what it's, remind you again what I show you with replacement. It's done with replacement. Okay, this means you go to pull the second king with replace means you replace the king. So you've got the same identical deck. On the second poll as you have on the first poll. So if the deck's identical, don't you have the same probability of pulling the king? There's still 4 kings in the deck. There's still 52 cards because you put this king back. You replaced it. So you've got 16 over 52 squared, and you can get a decimal for that. 0.0059. In 9.059. These two probabilities are independent. These probabilities, since they're identical, they're independent. Are independent. This probably does not depend on this one. The decks are identical. All right, so that's a version of a problem where the with replacement, without replacement, they use that exact language and it's obvious. On a lot of the rest of them, it's implied. But we're at 50 minutes. Do y'all want to play around with the problems and hit me with them again on Thursday? Or have you got the patience to see one where it's, say, implied? Do I have anybody with me still? Oh, okay.
Yeah.
Still got two people with me.
I'll say let's try, and then on Thursday we'll have more problems if we don't have.
Okay, so you want to try it, hit me with it on Thursday if you have any problems?
Yes, Professor C.
Okay. That go for everybody else?
Yes, sir.
All righty. Well, I appreciate you coming out this late on a Monday night. Hope this got you started. And yeah, on Thursday, we'll have a 12 p.m. and an 8 p.m. session. Hope y'all can make it. But I appreciate y'all coming out. Y'all have a good night.
So
Thank you.
quick question, Professor C. The exam school is still due open on Friday.
Going to give out the test on Friday, have the same format as test one. It'll be a Google form. 20 problems, 5 points each, and it'll be due Sunday.
Thank you.
All right. We will see y'all on Thursday, hopefully. Y'all have a good night.
Good night.